Hello everyone. Okay, hello everyone. In this video we're going to be talking about substitution reactions. Alright, so let's think about reactions in general and what exactly are we talking about when we think about a given chemical reaction. What kind of a scheme do we use for it, right? So we have really our reactant, right? And we could think of that as our starting material as well. But what we really refer to it is our substrate, right? Our substrate is really the same thing as our reactant. It is what we also call our starting material. All right, so that substrate is really turned over or converted into products. All right. But what causes the change of the substrate to the product is what we are going to refer to as our reagent, all right? So what you're going to be learning about in organic chemistry is a whole lot of reactions. One of them is substitution reactions. But what causes the change in that substrate to form the new product is what we refer to as a reagent, right? In general chemistry, what you did is you basically had two reactants. Well, one of the main differences that you'll notice is that we refer to one of them as our reagent, right? It's whatever is causing the change on the substrate itself. So that's something to keep in mind. So what exactly do we mean when we say substitution reaction? Something is being substituted in for something else. So what we have is really an exchange. But what are we exchanging? Functional groups. Remember, we learned about the different functional groups. So in substitution reaction, you're really having an exchange of one functional group for another, right? Of one functional group for another, right? So basically one functional group replaces another functional group, right? So let's take an example of a general scheme of a substitution reaction, right? So we're talking about functional groups, all right? So one example would be an alkyl halide, right? So if you had a halogen right here, that's an example of an alkyl halide, right? You have a carbon chain attached to a halogen. Well, you have the bromine right here, and suppose the bromine is replaced by something else, right? So now instead of the bromine, what you have, suppose, is an alcohol group, right? That's an example of a substitution reaction. You have one functional group, which is the halogen, is being exchanged for another functional group. Well, what would be the reagent in this case? It would be something that basically carries an alcohol group, right? So the reagent is, in this case, really sodium hydroxide, right? That could be one of the reagents. Water could be another reagent in this case. All right, well, when we carry a specific reaction, we typically carry it in a solvent system, right? And when we write a typical reaction scheme, we put the reagent on top and we put the solvent at the bottom, right? So if it's a one-step reaction, whatever we see at the bottom is typically our solvent. Another way that we put it is we actually put our reagent and then we put a dash to indicate in, and then our solvent, right? So think about it that you have a specific reagent in whatever solvent. So we either put them on top and the bottom of the arrow, or we use the dash. All right, so those are just some things to keep in mind. All right, so there are a number of things that we should consider when we take a look at this particular general reaction scheme, and that's bond polarity, right? So what makes a given substrate reactive enough that it forms a given product? The reagent plays a role, but the substrate itself does as well. Okay, so if you think about the bond between a carbon and a bromine, bromine carries a partial negative charge, carbon carries a partial positive charge, right? So one of the terms that we use in organic chemistry are nucleophiles and electrophiles, right? So I'm going to erase that. Just keep that in mind, right? Nucleophiles are atoms with a partial positive charge. You can think about that as being a nucleophile or a lone pair of electrons, or if something carries a negative charge. And we use that abbreviation Nu negative, right? You could think about it as when we talked about bases, right? Bases carry a negative charge or carry a lone pair of electrons. They're electron pair donors, so some nucleophiles are bases as well. Right, so here is nucleophiles. One of the other terms that we use is electrophiles, right? Atoms that are electron deficient, and we use the abbreviation E with a positive charge. Again, those are really indicating the charges, right? Whether or not you put the circle around it. So in this case, that carbon that bears a partial positive charge is acting as an electrophile, right? And an atom that carries a negative charge can attack an electrophile, right? That was much like an acid-base reaction where the base, which was electron-rich, attacked a proton or deprotonated a hydrogen without its electron, which was you could think about it as being an electrophile. Well, in substitution reaction, there is an exchange of functional groups. So something has to leave, and we call that our leaving group, right? And we're going to give it the abbreviation Lg, right? Substrate is also abbreviated as S. The product is abbreviated as P, right? So we say that the substrate is being converted into product. So I could have just wrote S going to P, right? But that's just a general scheme. Okay, so those are things to keep in mind. All right, So in this case, what left? Bromine left, right? So bromine is our leaving group. So I'm just gonna, bromine is gone, right? So in this case, bromine was our leaving group. The alcohol group replaced the bromine, so that was our nucleophile. And this particular carbon atom that carries a partial positive charge is our electrophile, right? The reaction and substitution reactions takes place at the carbon that's directly attached to the halogen, right? That's the electrophilic site, the atom that carries a partial positive charge where the reaction takes place, right? It's the carbon directly attached to the halogen, what we refer to also as the alpha carbon. All right, so something that we use in organic chemistry is reaction mechanisms, right? And we have seen those when we talked about acid-base reactions and resonance. And what we're showing is basically which bonds are being broken, which bonds are being formed, the order of events, right? So it does matter what step happened first and second. So we use mechanisms and we use curved arrows, right? So we call them sometimes curved arrow mechanisms. So we're using those curved arrow, and just like in acid-base, they're starting from the site that has the electrons to the site that is electron deficient, right? So think about those two pointing that that's where electrons are coming from, okay? And those are your two electrons, because later we'll use a different type of arrow, which is what we call a fishhook arrow, where we're only moving a single electron. So think about the arrow as two electrons, and that's typically for forming a bond or breaking a bond, okay? So now we're going to be talking about the mechanisms, and there's some sort of bonds that are being broken and formed. And what we use is curved arrow to show what is happening. And that's what we refer to as the mechanism. So there are really two basic steps in a mechanism of a substitution reaction, right? Two main steps. I'll just call them main steps, all right, that occur. One of the steps is really a nucleophilic attack. All right? So the nucleophile is really attacking that alpha carbon, all right? The carbon that's directly attached to the halogen. And one of the second steps that happens is for it to form a bond to that carbon, something has to leave, right? And what leaves is what we call the leaving group. So we have a nucleophilic attack, and then we also have the loss of a leaving group, right? Those are the basic two steps. Later, we'll see that they could be preceded by or end with what we call a proton transfer, right? And that is much like an acid-base reaction, right? A proton transfer can come either after the mechanism or before, right? So before or after a substitution reaction, you can either have a proton transfer at the beginning or at the end, but we'll talk about why, and when later on. So now there's two different types of substitution reactions, or two specific different types of mechanisms that depend on the substrate and depend on the reagent and also can depend on the solvent that we use. And the first type is known as an SN1 mechanism, right? That's substitution nucleophilic unimolecular, right? So that's really substitution nucleophilic, right? It requires a nucleophile, unimolecular, right? Meaning it's happening one step at a time. Those are the two main steps, and it happens one step at a time. Okay. Or we could have another type, which is known as substitution nucleophilic dimolecular. I'm actually going to keep this right here. I'm going to erase those. Hopefully you got this. All right, so we have substitution nucleophilic unimolecular, or we could have the different type, which is known as an SN2 mechanism, substitution nucleophilic bimolecular, right? Dimolecular. So substitution nucleophilic dimolecular. What exactly do those terms mean? One of the mechanism happens one step at a time, all right? So think about the one meaning one step at a time, right? So in other words, it's a stepwise mechanism, right? Whereas the dimolecular, both steps happen at the same time, right? Both steps occur at the same time or simultaneously. Both steps occur at the same time. Okay. So one is a concerted mechanism, and one is a stepwise mechanism. All right, so those are some of the main differences between those two. So now let's consider the substrate, right, for a moment. Okay, those pens are out. Okay, bromine. Bromine, and bromine, all right? What's the difference between the three different molecules? They're all alkyl halides if you're thinking about it in terms of functional groups, right? Then they're all alkyl halides, but the main difference is that this is a primary alkyl halide. The carbon that's directly attached to the leaving group is only attached to one other carbon, right? We look at the carbon attached to the leaving group is only attached to one other carbon. So it's a primary alkyl halide. The carbon directly attached to the leaving group, which we call the alpha carbon, is attached to two other groups. So that's an example of a secondary alkyl halide. Again, the carbon atom that's directly attached to the halogen is attached to three other groups. So that's a tertiary alkyl halide. Okay. So, gonna keep those two steps, but I actually want to reverse the numbers. So let's just, so sorry for that, but I'm gonna put the loss of a leaving group first, and then a nucleophilic attack. All right, 1, 2. It doesn't change anything about anything else that we said. One step at a time, meaning one of those steps will happen followed by the next. When both steps occur at the same time, those two steps will happen at the same time. So now we know the leaving group is a functional group that's attached to a carbon. There's differences in bond polarity. So if this bond was to be cleaved, think again about acid-base reactions or even resonance and electrons being delocalized. Electrons go to the more electronegative atom, the atom that would stabilize the charge best. And if we're breaking a bond, we're showing an arrow from the bond to the atom that takes the electrons, right? And in this case, what would form? Right? You have two electrons right here. Both electrons go to bromine. So now bromine leaves as an anion, right? Whereas that particular carbon now just lost an electron. One of those two electrons was for carbon, so it lost it, right? So now that carbon carries a positive charge. If you do the same right here, bromine is a leaving group. Then again, you have this carbon that just lost one of its two electrons, so it carries a positive charge. The same will apply right here, that you'll end up having a carbon with a positive charge. It doesn't matter if I do the positive charge here, here, or here. We're really referring to that carbon atom carrying the charge, right? Which is the same carbon atom that was directly attached to the bromine. Right, so we called those carbocations, right? So does it matter? Is one more stable than the other? Yes, well, the more substituted that carbocation is, the more stable it is, right? So tertiary alkyl halides, right? Tertiary alkyl halides end up forming tertiary carbocations. Secondary alkyl halides end up forming secondary carbocation. Primary alkyl halides end up forming primary carbocations. And if you wanted to think about which one is more stable or less stable, then the more substituted that carbocation, the more stable it is. So I'm just gonna, right, in terms of carbocation, so this would be the most stable, right? In general, they're not, that carbocation means an MTP orbital for that carbon. It does not have an octet, so they're not very stable. In general, they're very reactive, but if you compare primary, secondary to tertiary, tertiary are more stable. All right, so that's just some things to keep in mind, because when we talk about the loss of a leaving group, a carbocation is generated. So in an SN1 mechanism, it's a substitution nucleophilic unimolecular. It occurs one step at a time. So let's consider an example of substitution reaction. All right. So we're going to consider an SN1 mechanism, right? We're going to take a look at how does an SN1 mechanism actually take place. And we're going to use this same example that we had up here. Have a bond, right? Going to use water as our reagent, right? Water would be our solvent as well. And then this would be our final product. Well, in an SN1 mechanism, right, it happens one step at a time. So would you expect the nucleophilic attack to happen first, or would you expect the loss of a leaving group? So a reagent is our nucleophile. It's an atom with a lone pair of electrons, right? So would you expect water to form a bond first, or would you expect the halogen to leave first if it's one step at a time? Yeah, So water cannot attack first. Why not? Because that carbon atom already has 4 bonds. Remember, it has a hydrogen that we don't see. So if you also form a bond to water, you exceed an octet. So that is not possible. All right? So if you make sense of why you're making something happen, then organic chemistry becomes simpler. All right. So the very first step is really the loss of a leaving group. And you don't have to draw the hydrogen. It was just for me to show you why you can't have water attack first. Right? So you have the loss of a leaving group. So now bromine leaves as an anion, right? But bromine is taking those 2 electrons with it. One was for that particular carbon atom. So what we end up forming now is a carbocation, right? We have a carbon with a positive charge. Now the nucleophile can attack that carbocation that lacks an octet, right? So now we have water, which has lone pairs of electron. It can attack that particular carbon atom. But because it has an empty p orbital, it can attack from the top, or it can attack from the bottom. Avoid showing that it attacks to the charge, because then you'll fall into a lot of mistakes later on. It's forming a bond to the atom, yes, because the carbon is positively charged, but it's to the atom, not to the charge. I'm just going to draw it from the bottom. You could have drawn it from the top. Okay. So now you have this new bond to water. Now you still have the entire water molecule attached to it, right? But water now just donated one of its lone pair of electrons to form a bond. So now it carries a positive charge. So that's something to keep in mind, right? Now you could think about it as an acid-base reaction. You could deprotonate water to form the alcohol group. All right? You could deprotonate it using the leaving group, or typically the solvent. And if water is a reagent, our solvent is water as well, right? So what will happen is water will deprotonate. But if a bond is formed, a bond has to be broken. So this bond is broken and the electrons go to the oxygen. Then this is really our final product, right? But what left in this reaction is also hydronium ion, right? So if you like to write all your side products, then hydronium ion was formed in the process. Right, so that's an example of an SN1 mechanism. It's a stepwise mechanism. The loss of a leaving group happens first, and then the nucleophilic attack. It goes through a carbocation intermediate, and then you have water, right, which can be deprotonated using the reagent or the solvent, and then we form our final product, right? Okay, so now let's consider energy diagrams, something that we've seen in the past, right? So that's a reaction coordinate, right? Think about it as the progress of the reaction that is taking place. And this is the overall potential energy, right? As potential energy increases, something is less stable, right? And you have a reactant going into a product. And we have 2 aspects that we think about when we look at an energy diagram. It's really the reaction, the transition state, and the reaction intermediates, right? Every product that is formed in any one steps of the reaction that is consumed later in the reaction, those are our reaction intermediates. So this carbocation is an intermediate. This particular product is an intermediate as well. And then if you think about transition states, think about how many times did a bond form and was a bond formed and broken. And those are the different steps. There's the very first step, there's the second step, and there's the third step. So those really refer to your transition states. In this case, it was 3 steps. Do you always have that very last step? That's what we refer to it as a proton transfer. No, sometimes, all right? The 2 main steps are the loss of a leaving group and the nucleophilic attack. It may be preceded by a proton transfer, and we'll see an example of one, or a proton transfer can happen at the end, which is what we saw right here. So our starting material is really our substrate, right? And then we have our final product, okay? But what we have in between is the different steps that are taking place. We have the first step, the second step, the third step, right? Now, the very slowest step in the reaction that is really irreversible, right? Those reactions, you could think about them as being at equilibrium or reversible, but an irreversible step, the slowest step in the reaction is the loss of a leaving group. That's the rate determining step of that particular reaction, right? So that would be the one with the highest energy of activation, right? The slowest step in the reaction, the rate determining step, is the one with the highest energy of activation. That transition state is indicating the formation, how the bonds are being formed and broken, but then it forms an intermediate, which is this carbocation. So that's our intermediate. Our hills are the steps. Our valleys in a reaction coordinate are really our intermediates. But then there's a bond that forms between water and the carbocation. Okay, so this is just, not exactly to scale. Right? But this would be very quick, so its energy of activation is small. And then you have the proton transfer, which is even quicker, and then we form our final product. Okay? So this is the transition state. I'll just label 1, 2, 3. You can think about it, the first step, the second step, the third step, right? But this is the slowest step, the one with the highest energy of activation. And then those 2 points are really our reaction intermediates. So this would be the carbocation, and this could be the one with water. Okay? So that's an example of an energy diagram. So in an SN1 mechanism, that entire process is really dependent on the loss of a leaving group. So if we were to write out the rate of the reaction, then for an SN1 mechanism, the rate is equivalent to the rate constant times the concentration really of the substrate, right? It depends on the concentration of the substrate because it's the rate determining step or the loss of a leaving group. Okay, so I hope this was helpful so far. So now we're going to take a look at a different mechanism, an SN2 mechanism. It's dimolecular. Both steps, the loss of a leaving group and the nucleophilic attack, are happening at the same time. So what we'll notice is that it will not go through a carbocation intermediate, right? That is only for a stepwise mechanism, like an SN2 mechanism. I mean an SN1 mechanism, because it's stepwise. All right, so now let's take a look at an SN2 mechanism. All right, and we'll consider a similar example, right? So, bromine. I'm going to use sodium hydroxide, the alcohol group. Okay, so it is a concerted mechanism. Both steps, 1 and 2, are happening at the same time. The nucleophile has to carry a lone pair of electron or a negative charge. If you think about sodium hydroxide, sodium is a metal, oxygen is a non-metal. So it's like what you have really is a sodium and a hydroxide. So the hydroxide is really our nucleophile. Sodium is just the salt, part of the salt, right? Or the ionic bond. Sorry, not the salt. The ionic bond between sodium and hydroxide. So what we have is the alcohol group now, or the hydroxyl group, that's basically acting as a nucleophile. And it attacks the alpha carbon, which is the carbon directly attached to the leaving group, but it carries a negative charge. So it's a stronger nucleophile than water. Water is neutral, simply carries alone pairs of electrons, whereas hydroxide actually carries a charge, right? So it will attack but it's a strong enough nucleophile that it will force the leaving group out. So the loss of a leaving group and the nucleophilic attack, both steps happen at the same time. It's a concerted mechanism. And then we end up getting the final product, right? But now, because you don't have a carbocation, you actually have a carbon with 4 atoms, that alcohol group, or the nucleophile, will always do what we call a backside attack, right? So now, is that particular carbon a chiral center? No, because you have 2 methyls, right? So let's just make it into a chiral center. Okay, so now let's suppose this is on a wedge. Because the nucleophile comes in at the opposite, via a backside attack, what ends up happening once it pushes the leaving group out, you end up having an inversion of configuration. So if you have an S configuration, it ends up being R. If it was R, it ends up being S, right? So what we get in an SN2 mechanism is an inversion of configuration, right? Configuration. I'm just going to stop it at configuration. You get an inversion of configuration, right? You have a backside attack and you have an inversion of configuration. Okay. So what if you wanted to draw its energy diagram? Or what if you wanted to think about the rate of the reaction? What do you think the rate of the reaction for an SN2 would depend on? Does it matter how strong or weak the nucleophile is or the reagent, or does it only depend on the substrate? Depends on both, right? So the rate of the reaction depends on the substrate, but it also depends on the nucleophile or our reagent, right? Okay, so what if you wanted to draw the energy diagram? It's a single step. Everything is happening at a single step. So if you were to draw its energy diagram, you have our starting material, you have the transition state, and you have our final product. So this would be the product, and this would be So I actually made those two. I didn't make the inversion, so here we go. Otherwise, they were really the same configuration. Okay, so. Okay, and that's our transition state where bonds are being formed and broken. It was a single step, so there was one transition state. In this case, it was 1, 2, 3 steps. 1, 2, 3 different times when bonds are being formed and bonds are being broken. All right, so that's a general summary of substitution reactions, right? When does a proton transfer proceed? An SN1 or an SN2 mechanism. That is something that we have yet to talk about, but it has to do with when we have a poor leaving group. And an alcohol is a poor leaving group. We would have to protonate it first. So I think I have still some time. So what we're going to do is we're really going to summarize substitution reactions so far. Okay, so we're going to think about different aspects of it. We're going to think about our substrate. We're going to think about our reagent. What else happens in the reaction? What are other things that we need to keep in mind? Our substrate, our reagent, our solvent system, perhaps. All right? We could think about it as the reagent or as our nucleophile being weak or strong nucleophile. Okay, so I'm missing something, but I can't think of it at the moment. So let's compare SN1 versus SN2. All right. Well, SN1 mechanisms go through a carbocation. And we have said that primary carbocations are not stable. So SN1 mechanism really favors secondary and tertiary alkyl halides. So the substrate has to be a secondary or a tertiary alkyl halide. Whereas in an SN2 mechanism, because both steps happen at the same time, a tertiary alkyl halide would be too bulky, and because of steric interactions, it will not favor SN2 mechanism. So it really favors primary or secondary alkyl halide. Notice secondary alkyl halides are present in both SN1 and SN2. Okay, now what about when we think about the reagent, right, our nucleophile? Well, in an SN1 mechanism, the loss of a leaving group is the rate-determining step. So you don't want a very strong nucleophile to compete with the loss of a leaving group. So the reagent is typically a weak nucleophile, right? So in an SN1, we use a weak nucleophile, whereas in an SN2, it requires a strong nucleophile. All right, because SN1 mechanisms go through carbocation, right, and they're typically something that is protonated, not charged, they typically favor protic solvents, right? Something that has an OH or an NH bond. Whereas in an SN2 mechanisms, those favor aprotic solvents, because protic solvent may solvate that ion, right? So they do favor something that is polar, but aprotic, right? So it doesn't have an OH or an NH bond. Okay? So now let's take another example. We could probably do a couple of more minutes. Or actually, let's think about what makes a reagent strong versus weak, right? Why would we call something a weak nucleophile versus a strong nucleophile? Think about acids and bases, right? You think about a base, one that is charged versus one that is neutral. The one that is charged and carries, an extra electron that typically can act as a stronger base. That's the same case for nucleophiles. Something with a negative charge can be a stronger nucleophile. Right? You could think about them in terms of the mechanism as well, right? SN1 is one step at a time. SN2, both steps happen at the same time. So their mechanism is also different. All right, so in this case, we were really comparing SN1 to SN2, right? But we're going to look at the reagent, right? And in this case, our reagent is really our nucleophile, right? We could define them as being weak. Weak nucleophiles versus strong nucleophiles. So let's consider some examples. Okay, let's take a look at the simple example of water versus sodium hydroxide. What's the main difference? A hydrogen versus a sodium, but this is a polar covalent bond, right? Whereas sodium hydroxide is an ionic bond. So the sodium is negatively charged, and the hydroxide is, the sodium is positively charged, and the hydroxyl group is negatively charged. So that's a stronger nucleophile. And what you'll notice that the difference is really a hydrogen to a sodium, right? So sodium hydroxide and water. Methanol, it's a methyl attached to an alcohol group. Methanol is one example. I mean, I don't have to really draw this as a bond. I could just draw the hydrogen next to it. Okay? Or we could have sodium methoxide. Right? They're the same. One is a strong nucleophile, one is a weak nucleophile. Right? This is called really methanol. This is called sodium. I guess I should write the whole name. Sodium methoxide. And it's methoxide because it's attached to a methyl, CH3, and it's oxide because that oxygen is negatively charged. So a methoxide is really an oxygen that is negatively charged attached to a methyl group, right? And we typically abbreviate that methyl as Me. So that is common. Methoxide, really. OMe is methoxide, and the oxygen is negatively charged. You could see it written as sodium methoxide. Okay. What's the nucleophile in this case? It's the atom, right? That's directly attached, that has a lone pair of electrons. So that's sodium methoxide. Very similar to it is sodium ethoxide with an ethyl, and then it's abbreviated ET. All right, so it's easy to differentiate between weak and strong nucleophiles. The substrate, the solvent really dictates when it's secondary if you would do an SN1 or an SN2 mechanism. So now let's consider an example. All right, halogen sodium bromide versus hydrobromic acid as well. So now let's consider a different example. Right, so we have an alcohol group, and you treat that alcohol group with hydrobromic acid. All right, well, there's the very first thing you need to think about is that that particular alcohol group, look at the carbon that's directly attached to the alcohol group. It's a primary carbon or a primary alcohol group, right? It's only attached to one other group. So that means it has to be an SN1 mechanism, even if our reagent is not charged, even if we're not using sodium bromide. And one time we would use like hydrobromic acid as opposed to using sodium bromide, which is a stronger nucleophile, is that we have an alcohol group. An alcohol group is a poor leaving group because if the alcohol group was to leave, it would be a strong base, right? So they're never leaving groups in Orgo-1. You would have to protonate it. And that's when a proton transfer would precede an SN1 or an SN2 mechanism. When alcohol groups are, you know, what you're starting off with, because the very first step would have to be a proton transfer. So this is primary, which means it has to be an SN2 mechanism. But the alcohol is a poor leaving group. So the very first step that we have to do in this case is really take the hydrobromic acid and protonate the alcohol to make it into a better leaving group. So the alcohol is going to deprotonate hydrogen bromide. Those two electrons are going to go to the bromine. Now we just formed this new bond to the hydrogen, right? But now the oxygen carries a positive charge. Now water is an excellent leaving group. It's a better leaving group than halogens. It's an excellent leaving group. And now since it's an SN2 mechanism, we can now do both steps at the same time. The loss of a leaving group and the nucleophilic attack, right? And again, it's a backside attack. It's the opposite end of where that molecule is. Even if it's not a chiral center, we keep that idea of a backside attack, the opposite end of where that bond is. Okay, so now water is gone, and it's like you erased this bond, but what you did is formed a new bond to bromine. Right, so I'm going to show this new bond, and then we really added the bond to bromine, right? So if you're just predicting the product, get rid of your leaving group, replace it by the nucleophile from the reagents. All right, well, I hope this was somewhat helpful. I will see you next time.